Hello everyone, it's an honor for me to give a presentation today. I want to introduce a reverse turbo-Brayton cycle cryocooler for ZBO storage of liquid hydrogen in space to you. Liquid hydrogen is a high-specific impulse propellant, which is widely used in aerospace. Hydrogen storage is a key problem in the long-distance space exploration. In recent years, zero boil-off storage of cryogenic propellants is a significant storage technology for space exploration, where the cryocooler is used to achieve zero boil-off. However, it's difficult to achieve the large cooling capacity at 20 K in space. The reverse turbo-Brayton cycle cryocooler has the obvious advantages of large cooling capacity, low vibration, high reliability, and long life, which is used as the cryocooler in zero boil-off system. So in this study, we designed a reverse turbo-Brayton cycle cryocooler combining nitrogen and helium cycle is designed to provide the cooling capacity at 20 K and 90 K for liquid hydrogen and liquid oxygen. First of all, I want to show you research background and significance. Propellant storage in orbit is a technical basic for many space technologies, such as spaceflight. Cryogenic propellants used in aviation has low boiling point and are easy to evaporate. In order to achieve long-term storage in orbit, adiabatic storage is necessary. NASA's proposed propellant zero evaporation storage system combines passive insulation with active refrigeration to eliminate propellant gasification during in-orbit storage. The reverse turbo-Brayton cycle cryocooler structure used by NASA's ZBO system is shown at the left. The working medium is pressurized in the turbo compressor and then discharged heat through the stage post cooler, and then is further cooled by heat exchange with the low pressure working medium from the cooling screen in the refrigerator. Then it expands in the turbo expander and falls to the cooling temperature zone, and finally flows into the large cooling screen to provide cooling capacity for the storage tank. The high-speed helium centrifugal compressor shown in the right figure is one of the core equipment of reverse Brayton ultra-low temperature refrigeration system. Space application requires to be miniaturized, lightweight, and efficiency. NASA ZBO 3-stage high-speed minor helium working medium centrifugal compressor is shown at the right. There are many engineering applications of high-speed macrocentrifugal compressor abroad, and the main technology is permanent magnet synchronous motor and air floating bearing. Next, I will introduce the reverse turbo-Brayton cycle system. It has a helium cycle and a nitrogen cycle. The nitrogen cycle in the system can provide a cooling capacity of 20 volts at 90 K for liquid oxygen storage, while the helium cycle in the system can provide the cooling capacity of 5 volts at 20 K for liquid hydrogen storage. There are 3 centrifugal compressors and 1 expander in the nitrogen cycle. The expander is coaxial with the one of compressors which can recover the expansion work. There are 4 centrifugal compressors and 1 expander in the helium cycle. A heat exchanger is used to connect the nitrogen cycle and helium cycle. Therefore, the nitrogen cycle can provide the cooling capacity for the pre-cooling of the helium cycle. A microtube recuperation is used in the helium cycle to improve the heat transfer efficiency between hot and cold fluids. In addition, the cryocooler can also provide the cooling capacity of 200 watts at 90 K for liquid oxygen and 200 watts at 120 K for liquid methane with only the nitrogen cycle. The reverse turbo-Brayton cycle cryocooler in this study can achieve the zero boil-off storage of liquid hydrogen, oxygen, and methane in space. This work can provide the theoretical guidance for design of zero boil-off storage in long-distance space exploration. Next, I will show you the helium centrifugal compressor design and check in detail. The ZBO system defines the following parameters for the compression system. Total pressure ratio is 1.6. Total power consumption is lower than 2000 watts. Mass flow is 4 grams per second. Working medium is helium. Based on the above system pressure ratio and the efficiency requirements, the compressor design thermal parameters are shown in the following table. Centrifugal compressor design results are as follows. Impeller adopts closed impeller. Each stage is 8 main blades and 8 small blades, no pre-rotation. The diameter of each wheel is 21.9 to 28.3 mm, and the height of the outlet blades is 1.1 to 1.16 mm. Diffuser. The blade diffuser is dotted. All 4 stages have 15 blades. Volute. Asymmetrical circle section volute is used to reduce flow loss and envelope size. Centrifugal compressor design results are as follows. The width of whole machine is about 1.7 kg. The length of the main part is 166 mm, and the outer diameter is 87 mm. The bearing capacity is provided by herringbone groove ratio bearing and the spiral groove thrust bearing, with a total length of 102.6 mm and an axial diameter of 14.5 mm. First, I want to talk about the influence of internal leakage on compression characteristic. High-speed macro-centrifugal compressor is different from conventional compressor in that the relative size of interleakage gap is larger and the relative internal leakage amount is higher. The working medium at the impeller outlet leads to the impeller entrance among the wheel cover clearance, and the working medium at the impeller outlet leads to the compressor chamber or the chamber to the impeller outlets among the wheel back clearance. CFD simulation results show that internal leakage significantly changed the parameters of each section of the compressor and reduced the compression capacity of whole stage. The internal leakage changed the inlet working medium parameters and flow angle of the impeller, and changed the outlet parameters of impeller and caused additional flow loss from low pressure stage. The internal leakage reduces the impeller compression efficiency and internal pressure ratio. High-speed macro-centrifugal compressor has high internal leakage, which changes the compressor compression characteristic. Based on this, the original mathematical model is modified as follows. For local inflow or outflow of leaking working medium, modify local mass flow rate and temperature. The working medium leaking from the wheel cover clearance to the impeller entrance has a large circumferential velocity, so its influence on the working medium flow at the impeller entrance is regarded as causing a certain pre-rotation. The working fluid leaking from the clearance of low pressure will back to the impeller outlet changes the average circumferential velocity of the local original working fluid. In addition, local flow conditions were disrupted and additional flow loss were caused. The results of mathematical model solution is as follows. Solution results of original model without internal leakage. The original mathematical model is basically consistent with the CFD results, and the main differences are reflected in the flow angle of leaking edge section of the blade, the flow loss in the diffuser section, and the flow rate at the impeller outlets. Solution results of original model and modified model with internal leakage. The first level as an example, the total temperature of inlet and outlet, flow angle of each section, and total pressure of diffuser section in the modified mathematical model are closer to the CFD value. The total pressure ratio and total temperature ratio of the whole stage are more accurate based on the CFD results. And solution results of modified model with internal leakage. After modification, the total temperature and total pressure of each section of mathematical model are basically consistent with the CFD simulation results, and the flow angle at the leak edge of the impeller blade and the flow velocity at the outlet of impeller have certain deviation. The predicted value of impeller outlet total pressure by the mathematical model is higher than the CFD value. The predicted value of blade compression efficiency by the mathematical model is higher than by the CFD value, because the change of flow in the impeller passage caused by the internal leakage is concentrated on the side of wheel cover. However, as a one-dimensional model, the mathematical model simplifies and thinks that the whole section is uniformly affected by the internal leakage working medium. In addition, solution results a modified model under variable working conditions. The characteristic curves the mathematical model and CFD simulations are obviously different when they deviate far from the design condition. And that's all I have to show you. Thank you all.